life cycle. And that's standard stuff, the fish guys, this number is 10 to the 7th, but that's the way to that. So weight in pounds or weight in kilograms is condition factor length. So you use that to calculate how fast the fish are growing and how much one more day of growth would achieve. And so then the question is, like as a design example, calculate the maximum daily feed rate for 1,000 tilapia at 8 degrees, condition factor 760, and weight of 2 pounds. So first thing we got to do is we got to convert this 2 pounds back into a length, which is 13.81. Just rearranging that equation. Then our growth, we're going to grow them at 80 degrees. The base temperature, which they don't grow, is 65, and it takes 15 temperatures. 15 temperature units per inch of growth. So you calculate this out and look, 0.033 inches per day. So the weight day minus 1, see they were 13.81, now they're a little shorter, okay, and so you calculate their weight the day before, they're 1.986 pounds, so they used to weigh 2 pounds, 2 pounds minus 1.014 pounds per fish. How many fish do we have? 1,000 fish times their gain. So they're going to gain 14 pounds of feed per day times whatever their SDR is. So that becomes our feeding load. Once we have our feeding load, then we can calculate ammonia, carbon dioxide, oxygen, and TSS. And then boom. Okay, so then there's the other thing to design your tank is the density, what I call the density equation. And I really love this stuff. Okay, so the density as in kilograms per cubic meter is the length of the animal at harvest, or when you move into the next stage, divided by the C density factor. The C density factor doesn't change with length, it's fixed. So here's some density numbers we use for different fish. And so you plug in the density, I'm moving them or I'm harvesting them at some particular length, and that'll tell you how many kilograms per cubic meter you can have, how many fish you have, and it tells you how big the tank has to be. Does that make any sense? What else did I think? Okay, so there's that, just to give you a brief preview, and I only had 1 minute and 57 seconds. Now I have left 5 minutes for questions. What's in that next thing is this design example and a whole bunch of stuff. But here I want to get down to, we're doing just what I went through. And here's one of the key points. So this is like a 3-stage system, and the animals are going to be 193, 452, and that's a 3-stage system. Okay? And so then we're going to estimate our feed rates, feed per tank. Then we have to determine this controlling flow rate, dissolved oxygen, TAN, CO2, and nitrate. And we pick those numbers, and then we have to pick our effectiveness of the treatment system, which we get from manufacturer own personal experience. And then there's your equation, and you start calculating all those things, and you're going to end up. Let me just show you. Skip over here. Okay. So if you did a lot of calculations, you'll get to this point where you have the amount of flow required. Remember, Q times C plus P equals Q times C. So what's the Q required to maintain those target values in the fish tank that you selected with your consolidated graph? So it said TAN was 73, oxygen was 290, 7452. And then, of course, the other one there is hydraulic retention. So, as Bert was saying earlier, never use more than one exchange program, never more than one. And you're moving more and more towards 30-minute retention time, 15-minute retention time. Bert showed nice graphs on when you pick one. So, this says, okay, so what do you got to do, right? So if you chose, so that says my time is up. But it's not actually up because it's only, what time is it?
Yeah, fine.
That's what it does. It's not got a plan. So if this is with air, okay, and if you ran your system at 290, what's going to happen here? Say your TAN target was 1. Well, if you run, and you only need 73, so if you ran 290, it's just going to be better, right? It's going to be probably like 0.25 instead of your design target of 1. But what would happen if you ran it at 73 and said, oh, that's just too much, right? Well, you're going to die because the flow required 290 gallons per minute. So well, I just can't do that. So this is where you go back and say, oh, how do I change that CVS? So you go in and say, okay, I'm going to start using some pure oxygen. So you do the calculation and it'll say something like, oh, it had to be 16 milligrams per liter instead of 8. Okay? And so what I do is I start filling with those things until they're all about the same. Solids never is a controlling factor. But these three, in hydraulic retention time, I keep designing and I keep adjusting primarily on that oxygen concentration until I get it to where they're about the same. Okay? And then there's a whole bunch more things here. So, questions?
Well, first, thanks, Mike. Now you know what it's like to be a student. I only did it like 11 years. Questions?
And Brian actually put him across the finish line, finished his dissertation, but you live into my basement. Okay. No questions?
Now, what if somebody said, well, you ran through a whole lot of these real fast. Where can I find that information?
Yeah, where can you find that? Well, it's always in the elevator. Yeah, that's a good answer. But these presentations are going to be posted on the aesweb.org site. Okay? Because I listen to Dr. Worker. I mean, I'm pretty familiar with this stuff. I have to go back and look at some of those slides. Okay.